Hello everyone, this is Sukruti Joshi. Our today's topic for this particular video session is different applications of Sandmeyer reaction, Wolff-Kishner reduction and Cannizzaro reaction. So it is basically how we can utilize such type of organic name reactions for the synthesis of different products. It can be an organic product, it can be a kind of complex product. It is most widely used in various industries. So we will take a look on how actually such kind of reactions plays an important role in synthesis of different compounds. So we'll take a look on how the synthesis of that particular kind of compound is done. And we will also see that with which particular reaction we can get or we can synthesize or we can manufacture that particular product. So we will take a look on all these particular things here, and in various industries like in chemical industries, in various types of dyeing industries, in pharmaceutical industry and even in different types of industry, we actually use this type of name reactions widely. So we require here that particular reaction and how it will be used for the synthesis purpose. So first of all, we will take a look on synthesis of phenol. That what is the actual use of phenol here? So we will use phenol in various types of organic reactions. It plays a very important role. So let's take a look here that where and what do you understand by phenol actually. So an organic compound which is aromatic in nature with the structural formula C6H5OH. So it basically contains OH group on itself. It is white crystalline rock that is very volatile in nature and very hazardous also. So that particular compound is known as phenol. The molecule has a phenyl group which is C6H5 attached to a hydroxy group that is OH group. So C6H5 will be attached with OH group. They both combines with each other and forms C6H5OH, which is known as phenol. It is slightly acidic in nature and needs careful handling due to its tendency for causing chemical burns. It has a very high tendency of causing chemical burns as it's volatile in nature plus acidic in nature. This will create certain type of problems in handling of phenol. So phenol is extremely reactive to electrophilic aromatic substitution as the oxygen atoms pi electrons give electron density into the ring. So by this overall approach, several groups can be attached to the ring through halogenation, through sulfonation, through acylation and other methods. So it can be said that it will generally follows electrophilic substitution process or basically it's electrophilic aromatic substitution process. So in general, in substitution reaction, what we will do is we will insert one group or one atom and we will remove that particular or another group or atom from that compound. So in general, it can be said that substitution reaction means here the electrophilic substitution reaction specifically means we are inserting one particular electrophile. So here the attacking group will be an electrophile and it will replace any other one or any highly electronegative atom from the compound. So this is how it will work basically. However, phenol's ring is so powerfully activated that the second only to aniline that chlorination or bromination of phenol will lead to replacement on all carbon atoms, that means on para and ortho to the hydroxy group, not only on one carbon. So this shows that how actually phenol will behave. It reacts with dilute nitric acid at room temperature to produce a mixture of 2-nitrophenol and 4-nitrophenol, while with concentrated nitric acid, many nitro groups gets replaced on the ring to produce 2,4,6 trinitrophenol. That 2,4,6 trinitrophenol is also known as picric acid. And picric acid is most widely used in dyeing industry, right, to get the yellow color. So that is basically where we can get different shades of yellow through this picric acid. In this manner, this particular ring, this particular substitution gives us an idea that which kind of groups can be attached or it can be substituted. Now let's see that how it goes. So preparation of phenols from haloarenes. So this is again an example that chlorobenzene is an example of haloarenes, which is made by mono replacement of the benzene ring. So here, how chlorination occurs. So what will happen there? H will be removed and 1 Cl will be entered. So when chlorobenzene is reacted with sodium hydroxide at 623 Kelvin and 320 atm, sodium phenoxide will be formed. Finally, sodium phenoxide on acidification makes phenols. So this is how the preparation of phenols can be done through haloarenes. Okay, so haloarenes, that means contains halogen group and aromatic ring. So aromatic ring which contains halogen group, that will be included here. Okay. Another one is preparation of phenols from diazonium salts. So when an aromatic primary amine is fused with nitrous acid, that is basically nitrous, so in the presence of HCl, which is NaNO2 plus HCl, acid at 273 to 278 Kelvin, diazonium salts are gained, and these diazonium salts are extremely reactive in nature, which when warming with water, this particular diazonium salts to end hydrolyze to phenols. And these phenols can also be acquired from diazonium salts by treating it with dilute acids. You can use HNO3, that is diluted HNO3. You can use here dilute HCl or dilute H2SO4 also, but they require proper conditions to convert that particular diazonium salt into our phenol. So that requires that particular parameters. Now, as you can see here, we have one reaction. So we are converting aniline to phenol. So basically, we will take a main substrate, that is aniline. We will react aniline with HCl. So that HCl will give rise to, or the particular combination will give rise to benzene diazonium chloride. So as you can see, N2 plus and Cl minus groups are attached. Then it will react with, or it will give rise to H2O. It will basically attack or reacts with H2O, warm H2O. So warm water has to be there. Then it will convert itself into OH. Right? So in this manner, that particular ring contains first of all NH2 group, and then it will contain, or it will convert itself into OH. So in this manner, as you can see, aniline gets converted to OH minus, and 2 and 2 are removed. Our next one is synthesis of thioethers. So transformation of aryl alcohols into high value functionalized aromatic compounds by selective cleavage and functionalization of the aryl OH bond is of crucial importance for us. It plays a very important role, right, in any particular kind of industry. So here, aryl nitriles are widely found in natural products, in different pharmaceuticals, in agrochemicals, in dyes and in herbicides. Moreover, because the cyano group can be easily converted into various functional groups, aryl nitriles are important intermediates in synthetic organic chemistry. So now let's see that synthesis of polyols and how it goes. Polyols can either polyether polyols or polyester polyols. So generally they will take part as polyether polyols or polyester polyols. Polyether polyols are made by the reaction of epoxides with compounds having active hydrogen atom. Okay, generally the formation of polyether polyols are done by reacting epoxides with certain compounds which contain active hydrogen atom. While polyester polyols are made up by the polycondensation reaction of multifunctional carboxylic acids as well as polyhydroxyl compounds. They can be either further characterized or categorized according to their use or their basically end uses. So higher molecular weight polyols with molecular weights from 2000 to 10,000 are used to make more flexible PUs. While other one which contains less molecular weight, they will be used afterwards. As you can see, this shows you two different examples or two different structures of polyols which are generally used and which are most widely used in different industries. Now let's see applications of Wolff-Kishner reduction. So Wolff-Kishner reduction has a broad range of applications. Some of them includes organic synthesis of multi-walled carbon nanotubes, synthesis of functionalized imidazole substrates, etc. So here we need to take into consideration that certain carbon nanotubes are formed using Wolff-Kishner reduction only. The next one will be synthesis of nitriles. So one of the most common occurrences of nitriles is in nitrile rubber. And that particular rubber is a synthetic copolymer of acrylonitrile and butadiene. This form of rubber is highly resistant to chemicals and is used to make protective gloves, glues, seals, etc. While amygdalin is naturally occurring molecule which contains certain plants to protect themselves against herbivores and insecticides. Now let's see that how it can be formed from an aldehyde or a ketone. So you can see that when we react aldehyde or ketone with NaCl and NH2O+, we get cyanohydride. So that is basically a formation of nitrile group. Similar way, nitrile is formed by an SN2 reaction between primary and secondary alkyl halides and cyano or sodium cyanide. So RCH2Br reacts with NaCN, gives rise to RCH2CN plus NaBr. So in this manner, we can form this particular one, which is RCH2CN, right? So that is again one kind of nitrile. This is all for this session. Next we will see in our next sessions. Thank you so much everyone.